Okay, what is this one? Let's start with, I'll just note it. I'm going to be switching in between, I guess, 2018 exam 3 ST and 2019 exam 3 PR. So I'm just going to write, I'll write 18 ST for any problem from that exam, 19 PR for any problem from that. I'm probably only going to pick a few problems from the other one just to save time. Okay, guess we'll get started. Let's start with number 1 here. What is this? Okay, so which of the following molecules will exist with the highest percentage of enol form at equilibrium? Which will have the least? Explain. Okay, so let's look at all of these here. Let's zoom in a little. Right, so we have a couple of different ones. Let's start with the first one, right? Enol is essentially just a intramolecular proton transfer, really, right? All you're really doing is changing this proton's location and the double bond's location, right? So a quick way to kind of tautomerize, right, will be simply this H here is now going to be here, which means this double bond here, right, we'll make that a single bond. It's now going to be there, right? So the resulting enol will look like this, right? This is one of those examples from the textbook, and probably I would assume in lecture too, why one of the few enols that exists in its enol form, right? Let's do the next one. Here it's symmetrical, right? It doesn't matter which side you pick, right? Make that OH. And double bond should be OH. And then methyl groups. So it should be like this. Let me make that a little nicer. OH there and double bond. And then the last one, same thing, doesn't matter. Could make this technically CH2, double bond, single bond, OH. And we get boom, right? And now essentially we're just kind of what's the driving force for tautomerization, right? So you could do a couple of different stuff. You could use REO factors to a degree, then you could do stuff like aromaticity and conjugation. Those are kind of usually in these kind of equilibrium or stability type questions. Those are like basically all the ways you could qualitatively analyze something, right? So for the first one, we go from something that is, well, it is conjugated, right? So you have 1, 2, 3 pi bonds conjugated, right? But the enol form, right, we form that benzene ring, right? So that's aromatic stabilized, right? So, I mean, right now I'm not going to rank them. Let's just look at the next one. So we could just make a note here. We have aromaticity present. Here, right, we have, we're going from, let me erase this now, right? These carbonyls are technically isolated, right? So now going from to this form, right, now we have an alkene that is in direct conjugation with there. So you have electron density kind of spread over 1, 2, 3, 4 atoms, right? And then the last one, right, you kind of just went from just the regular old, that's acetone, right, to just its enol form, right? There's not really any stabilizing factors there, right? So here, let me just write conjugation, right? And here you could write no additional stabilizing factors. If anything, right, yeah, it's di substituted too, right? And it's nothing really that kind of stabilizes this alkene, right? Particularly, and it's probably going to be very not reactive, but it's not going to be stable enough for it to stay in that form, right? So really what you have to do is you could automatically label that one, I guess that would be 3, right? And then really you just have to decide between aromaticity and conjugation, right? Now, aromaticity is conjugation, right? Because the whole thing of an aromatic system is there's multiple pi bonds that are conjugated with each other. The difference is because when you're in a cyclic structure, you have additional stabilizing factors, right? We learned this in the chapters 17, 18, right? So aromatic stabilization is just kind of a tier above regular conjugation, right? So whenever you form aromatic systems, right? Remember like the question we did with like, the double bond in between something, like those two things, right? The same kind of thing applies here, right? Is where we're forming something aromatic from something that wasn't, right? So we're increasing stabilization here, right? And that way, you could kind of rank 1 as this 1. Oh, wow, they all work out to be 1, 2, and 3, right? And that would be your reasoning, right? You would kind of just, draw the structures and explain, right? And then really all you have to do is compare 1 and 2 in this case, right? We can convert using, it doesn't matter which way you could, the main thing, that's why I said it's understanding what a tautomer is, right? A tautomer for any carbonyl, right? Whatever the structure might be, I don't know, doesn't matter what this is. Some R group here, some group here. A tautomer is literally any alpha proton, right? Let's make this pink, right? It has now changed its place. So really it's the location of the unsaturation and the proton have changed. And it's basically swapping between a carbon and oxygen, right? So the tautomer of this, right, would look like, it doesn't matter how you got it, whether base or acid, right? Well, let me actually keep that like this. So now this double bond here, because that lost the hydrogen, and we're good. Call this R, right? And make that like this. And now the hydrogen has just changed its position, right? So in terms of molecular structure, they're the same, right? Tautomers, right? In terms of kind of, I guess, properties, right? They might be different, right? So I guess they're constitutional isomers, right? But all that's essentially happening is that proton is changing its location from a carbon to an oxygen, right? So that's why it's one of those things you have to be able to do kind of really quickly, right? Because it's going to save you time on your exam instead of, working out a mechanism, going through an enolate or enol, right? It's just going to waste time. So yeah, that's really how it's like all these ranking questions before, right? You either use some form of ARIO, right? Then on top of ARIO, we learned about conjugation. That was chapter 14 or 16, I think. And then aromaticity. These are generally, I butchered that spelling, but ways to qualitatively assess molecules, right? Those kind of, really it all still comes under ARIO, right? But those are ways we could kind of, without having to do experiments and get actual numbers, we could kind of generalize how we expect a molecule to behave, right? Okay, so let's do number 2 from the other exam. So this is going to be, what is this, 2019? Wait, hold up. I have too many exams opened up. I have RS open and PR opened. They're the same. Which one did I want to do? I'm going to do PR because the synthesis is better in there. Okay. Let me copy these molecules. Actually, I'll copy them one by one. Okay, so here we have one of those carbohydrates, right? So, or what does this say? Convert each open chain monosaccharide Fischer projection into its lower energy ring form. Show stereochemistry. Designate naturally occurring or non-naturally occurring. So once again, this was 19 PR number 2. And I guess we could call this one A, right? Let's zoom out a little. Okay, so the carbohydrate questions, we didn't get to this in recitation, but you guys should have learned this. Basically, right, kind of one of the cool things about sugars, right, is they go from the cyclic to open chain form, right? And that's very important in terms of your body processes, right? Like, I don't know, I think glycolysis and the reverse thing, that all involves basically this, right? And its ability to convert between these two forms, right? So these are pretty simple in terms of if you get the kind of strategy down, right? Obviously, we won't get to, I don't have a full lesson on this, but I think, let me see. So from last semester, I should have a recording if you guys want to watch that. But basically how I always do these questions is first thing I do, right, is kind of swap out this. Actually, before I even do that, I just realized you asked another question. Designate naturally occurring or non-naturally occurring. So based off the structure of this molecule, and I'll give you kind of a hint where the circle is this naturally occurring or is this non-natural? So is it a D sugar, aka natural, or is it an L sugar? Okay, those who answer natural, why? Right, OH. It's literally that simple, right? So whenever we have a Fisher projection, right, if the final OH group, right, so you have your aldehyde here, right, then you have one, so this would be 1, 2, 3, 4, 5, right? And this technically is 6, but basically the fifth carbon, right? If the OH is on the right of the Fisher, right, we designate that as D sugars, and they're naturally occurring, what we find in nature, right? And when it's on the left, it is non-natural, right? And it's really that simple in terms of notation. That's why I think this is, I want to say, I forgot Fisher's first name, but a lot of his work, like, you know, the guy, this is all named after, he did majority of his work on carbohydrates. That's why he designed the system and all this stuff, right? It's pretty easy way to kind of remember this. Now, how to get the structure right, this is kind of what I do, right? I mean, you could redraw it or whatever. I have to redraw it here just to show this properly, but HOH, HOH, and one more, right? So what I do, right, is to make sure you can never mess up the location of the kind of substituents, right, is you can just remember this is at the end of this chain of this open chain molecule, right? So if you do a rotation, right, because remember technically these are wedges, right? This is on a dash, right? If you do a rotation, all you're doing is kind of changing the orientation of what group is at the end, right? So if you do, I guess, a clockwise rotation, the OH will be on the bottom. Then that would mean this is the CH2OH group, right? This is now our hydrogen, right? Because that moved over that way. And this is going to be our OH, right? And now it'll always be easy to kind of remember what is going to be what, right? So in order to get the actual thing, right, we deprotonate it there, right? Oops, let's make that a little better. That attacks there. That's going to open this up, right? And essentially, we're going to have a bond. This is the bond, right? This I'm going to put on that squiggly to indicate that it's anomeric, right? Because it could either be up or down depending on, well, why will it be up and down? Let me ask you guys that. What's the reasoning for that? Why does that end up being anomeric? No, it's not alpha or beta. Think about the nature of the attack. Excuse me. There we go. Nabila got it, right? So it's a carbonyl. It's sp2 hybridized. It's flat, right? It has a top face and a bottom face, right? So the oxygen can come in from the bottom or it could come in from the top depending on how it conforms, right? And that's why we end up with two different things. I mean, the rest of you guys are fine in terms of terminology, but that's the reasoning why it ends up being anomeric, right? So we could leave that as anomeric, right? So you could label, I always like labeling, let's use white, I guess. 1, right? So this will be carbon 2, 3, 4, 5, and then this will be 6. Technically that's 7, but in terms of labeling, this is what's going to form our ring, right? And now how you remember what side is what, right, is everything on the left, right? So left is going to be up, right? And then everything on the right is going to be down, right? Technically, you could do it the other way too, but this is kind of how I was taught to do it, and I think how most people do it, right? So groups on the right, and the reason also is because you're going to see most of the groups end up in, I guess, equatorial positions, or maximize equatorial this way. And now you could just draw the cyclo. I guess technically it's a furan ring. So let's draw that pink as well. I gotta make this a little nice looking. Do it over here. Okay, that's as good as it's gonna get for me. Okay, so this is technically oxygen is 1, right? It is bonded to carbon 2. At carbon 2, we have an anomeric hydroxyl group, right? At carbon 3, we have OH on the left side. So is it going to be axial or equatorial here? So let me also label these inside here. So right now we are 1, 2, this is going to be 3 here. Talking about this OH here. So maybe let's go over some rings. So cyclohexane ring, right? Axial up, equatorial down. Equatorial up, axial down. Axial up, equatorial down. Axial down, equatorial up. Equatorial down, axial up, right? Axial down, equatorial up. We are at this position here. What did I say? Things on the left are going to be up, right? So it's not going to be equatorial, it's going to be axial, right? So make sure you have your kind of base, because it just makes it easier to remember where the CH2OH group is going to go. You could have probably, I mean, if you wanted to, you could have drawn it on this side. Basically, for all D sugars, right, you could just think of that CH2OH group. It's always going to be up, I guess, right? And then for L sugars, that CH2OH group is going to be down, right? But to bring back what I said here, oops, why is this eraser? Damn it. Little, here we go. So we're at carbon 3. Which position is up? Axial or equatorial here? Axial. I just drew the thing, right? Right here, right? So maybe touch up on the cyclohexanes, right? The only difference between this and a regular cyclohexane is there's an oxygen at position 1. The way the substituent works are the exact same way because it's a chair, right? So if that is on the left, it's going to go up. So let's try to draw this as nice as we can. Okay, carbon 4, next one over. It's going to be down, right? So it's going to be axial. Okay. Carbon 5. Axial, right? OH. And then the CH2OH group, right, is going to be equatorial. Try not to butcher that there. And that's your ring, right? My 3D-ness is a little bit off, but it's close enough, right? Like I said, the main thing is like, I know the question says like the lowest energy form, but you know, that doesn't mean flip around everything to make it equatorial, just as is, right? How it's going to exist. And this is how it's going to exist. I mean, technically, if you flip it, well, actually, this would actually be pretty stable as it is. The reason being is because you have this intermolecular hydrogen bonding when they're axial. So that's actually a stabilizing factor. Obviously, if you have them all equatorial, that's not bad. That's why glucose is like, you know, the God molecule, right? Or like the God sugar, right? Because every OH group is equatorial, right? But whatever this one is, I don't know which one this is. Let's actually check the textbook. I have a list of all these sugars. Let's see if we could find it. We had what? 1, 2, 1, 2. This is idose, D-idose, this sugar, right? So that's how it would exist in nature, right? So that's how I would always do these questions is I label, I kind of switch the bottom to make sure everything's on the right side, and then I use this left side up, right side down thing, right? And you can usually always get the right structure that way, right? It has so far never failed in terms of getting the proper chair conformation, right? Just for those who might have had issues with axial equatorial, maybe just review your basic chair structure. Funny enough, that white chair structure there looks a lot better than this other ring I drew. That's funny. Okay, let's do the other one from this exam, which is your 1, 2, 3. 5. So I guess it's a ribose technically, or pyranose ring. Yeah, so you indicate the OH as squiggly, right? Or anomeric, right? Because that's the anomeric carbon, right? So we can't definitively kind of, say whether it's axial or equatorial. It depends on the face of attack, right? So the best way to describe that is with that squiggly line, right? Because that indicates that it can be either up or down on that carbon, right? Because it's the anomeric carbon, right? So as long as on the anomeric carbon, right, it should always be a squiggly, right? Unless you want to draw both structures with its up and down, but that's just wasting time, right? Okay, let me copy and paste the other structure here. This is from same thing, 2019 PR. Yeah, when we get to question, I guess 4, I'll give everyone, because that one I'll let everyone take a few minutes and maybe attempt them if they haven't already done it. Okay, so this is, I guess we'll call this B, the same exam. This is 19 PR, number 2, same problem. Now we have a ketose, right? So these are called aldoses up here because the terminal group here has or I should say the terminal carbonyl is an aldehyde. Here we technically have a ketone, right? Now this might be a little kind of confusing because, it's already methylated, right? But you could also kind of think of this as it got methylated later, right? So it's not like you have to, specifically say whether it's what's it called? When you like, I know like this is where I remember, because I remember this exam because someone talked about it, it was very confusing, right? Just treat it as OH and then just add the OMe as you draw the structure, right? Because that's really what he's looking for. Like it's a little confusing in its open chain form since it's already methylated. You're like, oh, well, technically it can't do an attack. I mean, it could. It's just, it's just the way it's drawn, right? So just kind of consider that as similar to OH, right? So here, right, technically it would be this one here. So, oh, first of all, is this natural or non-natural?
Natural.
Right. So we'll say this is a D sugar, natural. I don't know if I wrote it on the other one. Right here too, D sugar, natural. Okay, right now, let's rotate this again. Let me redraw it. OH, one more. Oh wait, no, we're gonna do the rotation. Okay, so now we rotate here, right? So if we do this clockwise rotation, this OH is gonna be there. It's gonna put a lone pair there. That means our CH2 OMe is here, and this is our hydrogen. Form our bond here. Except now it's gonna kick up here, right? This kicks up, right? Now, technically, we have, once again, depends on the face, right? If this went top or bottom, right? The CH2OMe could be up and the OH that forms could be down, right? And if it went the other way, this would be up and the other one would be down, right? So technically, these are both anomeric. So you could put a squiggly here, you could put a squiggly there, right? We're unsure of which direction at the anomeric carbon both the groups there are, right? So let's do a labeling. 1, this is carbon 2, 3, 4, 5. You can't draw a chair here, so we could do like a kind of a pseudo Haworth projection technically, right? I mean, actually, I don't know. Well, it's not really technically. I guess this is Haworth actually. I don't know if that's what it's called. I know for Haworth is for 6 members. I don't know if they're called the same for 5 membered. Let's do this pink again. So O, let's just draw. We have 1, 2, 3, 4, 5. So let's go. I want to bold this. I don't think it really matters too much, right? Let's do labeling here. Right, 1, 2, 3, 4, and 5. Okay, so 1 is bonded to 2, right? We have 2 anomeric substituents there, right? So here, it's actually, let's put this on top. Doesn't matter, but just because it was like that over there. Okay, so those are anomeric. So on carbon 3, right, we said, maybe let me write it down here again. Left is up, right is down. So on this one, is it going to be, well, we're not going to use actual and equatorial, right? So up generally, what do we use for that? Wedges or dashes? Wedges, right? So if it's on the left side, it's going to be up on a wedge, right? So on carbon 3, we have a wedged out OMe group. OMe on carbon 4, is it gonna, the OMe, is it gonna be on a dash or a wedge? Pretty sure this is the same exact question from the other exam. The only difference was the first sugar. So OMe. And then carbon 5, CH2OMe. Is it going to be up or down? Yep, wedge, right? Right, just remember when you're drawing that bond, right, you're drawing it to carbon, right? Don't write it like this, right? That's incorrect, right? Make sure whenever you're drawing any line, wedge, dash, regular line, visible line, right? All bonds to the corresponding atom, right? So make sure you start with the carbon there, right? Yeah, that should be it. Yeah, for the only time you'll make a chair conformation is when you have a 6-membered ring. Those are the only ones that, I mean, technically well, it's not really a chair. You have like fold in and half bowed and stuff like that. But the 5-membered rings conform. They just never conform to what we call the chair, right? That's specific to 6-membered rings, whether they're carbon, nitrogen, oxygen, doesn't matter, right? If you have a 6-membered ring, it could form a chair conformation because there's enough space in there for it to conform that way and get the best possible angles, right? Why did that oxygen attack the second carbon instead of the carbon? The double bond oxygen, the from the carbonyl is this, right? I removed the double bond because it attacked, right? It pushed its electron up, it got protonated, right? So the carbonyl is always the electrophilic carbon, right? So I did that earlier, right? So that's what happened now, right? Hopefully that clears that up. But you could always view it back in the recoil. Here you go, right? It's on the side here, right? So this attacked, right? Push it up, right? That becomes O minus, that gets protonated, that becomes our OH, the CH2OMe remains the same, right? So yes, the carbonyl is always the one that changed to OH. The difference here, right, compared to the 6-membered sugar, right, is there are 2 substituents here, right? So here, the same thing, this is the carbonyl. This is the carbonyl. The only difference is because this is a ketone, right, instead of a hydrogen here, right, we have an anomeric hydrogen, we have an anomeric CH2OMe group. That's it, right? Okay, let's do to the acidity question from this exam too. We'll do it from both exams. No, it does have stereochemistry, right? It's just not not defined. That's what the squiggly means. Okay, I mean, I'll give people like 2-3 minutes to answer. If you want, you could private message me your rankings. So you can go left to right if you want to send me them. So don't post them in the direct chat. Just if you want me to confirm. Well, I'm not going to confirm. I just want to kind of see what people got. But those who didn't do this, right? You could take a few minutes to do it. Like 3-4 minutes, 3 minutes. Okay, I got a lot of varying answers. Let's do it. Okay, we could always draw a conjugate base if you want, or just analyze it as is, but well, screw it. Let's draw the conjugate bases. Wait, which exam was this from? 2019 PR. Just make sure I keep marking it for you guys here. 19 PR, right? Okay, so here we have this, right? This would look like that. Methyl there. Here we have and last one. Only one person got it right. There we go. Those are conjugate bases. Now we can apply ARIO. What's the first thing in ARIO? It's what seems like a lot of the people forgot that part. Atom, right? So you see where I'm going with this, right? That's going to always take precedence. Doesn't matter what kind of conjugation you have, what kind of, I mean, maybe experimentally, you could maybe say, but as far as we're concerned, as far as you guys learned, right? Qualitatively, how we do this is based off ARIO, right? Atom takes the highest precedence, right? Let's call these A, B, C, and D, right? And as Madrona said, right? A, B, and D have it all on a carbon, right? C has it on an oxygen. So directly the negative charge itself is stabilized best on an oxygen. It's more electronegative than atom, um, than any carbon, right? So even though the other ones, yeah, they have additional stabilizing factors, right? The atom itself is going to take priority, right? So this one is going to be ranked 1, right? Because that's methanol, right? It's pretty acidic, right? I mean, the rest of these, their protons are fairly acidic, but they're going to be far less because they're coming off a carbon. It's harder to deprotonate. You're going to need a very strong base to deprotonate. Yeah, think about it this way too, logically, right? All of these deprotonations require some sort of extremely strong base. But methanol, if you put it in water, right, it can deprotonate into its conjugate base easily, right? There's that equilibrium between CH, the methoxide, and methanol, right? So let's keep going, right? We could also mark 4, right, is going to be the aldehyde protons. We know aldehyde protons are not acidic. The reason being, if we just look at this direct structure, right, this is a carbon that we know wants to be essentially electrophilic, right? And now it has a direct negative charge on it, right? So the chances, not the chances, the likelihood of this aldehyde ever getting deprotonated is very little because you're going to create an extremely unstable species right here, right? So this is going to be number 4, right? Because this is, like I said, right? You're creating something, something that will never want to be created because that carbon wants to be positive, and now you put a direct lone pair on it, right? And that's why we know aldehyde protons are far less acidic compared to the alpha protons, right? For that reason, right? So that can be number 4, and now you're really left between A and D, and there's really one main difference there is the atom's the same. The only thing that's different is kind of the resonance, the withdrawing groups, right? So A just has 1 carbonyl, right? So you have, what is it? This way, right? You could think of that as electron withdrawing here, right? When you form this can go this way, right? Or it can go this way. It's better stabilized, right? Because the lone pair can be spread across, what is that? 1, 2, 3, 4, 5 atoms versus 3 atoms, right? So D, right, D's base is more stable, therefore D, the original molecule, is more acidic, right? So this will be 2, this will be 3, right? So yeah, it's better delocalized because there's 2 electron withdrawing groups as opposed to 1. Yeah, you could confirm that with your professor. I think that should be right. And if I'm wrong, well, then I'm wrong. But that's the logic I would use to approach this question. It's a simple REO, right? I think that should be right. Okay. Let's do the acidity question from the other exam. This one is 2018. This is 18 ST, right? Okay, same thing again. Could draw out some conjugate bases. And last one. Oh, you don't even have to do an explanation here. Well, you guys got that for free then. Okay. All right. So, well, yeah, you guys have the answer key for this one. So obviously everyone should know the answers, but let's just go over why, right? So first of all of them are on carbons, so we can't use the atom priority anymore. Right now, we're going to kind of compare what one has over the other. I personally like to look at this in terms of electron withdrawing and donating groups, which kind of comes under resonance, right? Oh, whoops, I forgot the thing here, right? So out of all of these, right, let's label them A, B, C, and D again. Which one of these has an electron donating group? No, I wasn't saying you looked at the answer key. I'm saying there's no point putting the answer because I'm saying everyone has access to the answers. I'm sure you might have worked it out. But which one has an electron donating group? Which one is the only one pushing? Well,
C, because of the lone pair on the oxygen.
Well, C is still a withdrawing. It's just, well, we're going to get into what, but it's still withdrawing because directly next to the negative charge is a carbonyl, right? That's a withdrawing group. It's not as strong because of other reasons, right? But this one, right? This
the A,
OME,
yeah.
right? It's an available lone pair, right? It's, remember, OH, OMEs, like OR groups, right? They're electron donating. We could right off the bat say that that one's going to be the weakest because this conjugate base here, right now we have basically more electron density being pushed towards it, right? There's nothing withdrawing it here, right? It's only kind of pushing in there, right? You could think of this as like an O-alkyl group, right? Pushing in electron density, right? Even if it's one carbon away, right? Technically we have this one carbon in between, but this entire group is electron rich, right? It's not doing anything to withdraw electron density, right? So automatically we could label that as 4, right? Now we got to compare the rest. And what's the difference here, right, is kind of amount of carbonyls is the first thing we could look at. B and C only have one carbonyl next to the negative charge. And as we saw earlier, right, yeah, see, that's why this is the main thing is I saw this has OMEs. That's what I'm saying. Confirm this with your professor, this question, because I mean, it's still electron withdrawing. I think it should be more than the ketone. But yeah, confirm that with your professor just to be sure. But anyways, this one, right, we have just ketone groups. We don't have esters, but still they're very electron withdrawing compared to these two, which has this one carbonyl versus 2. So here, same thing, more delocalization, right, more electron withdrawing, which means that negative charge is better stabilized, right? So we could automatically kind of rank this as 1, right? And now it's really B and C where you have to remember that carboxylic acid, the kind of electrophilicity kind of stuff, right? Is that here, right, you have a partially positive carbon, right? We'll call this, let's say this is plus, right? But in an ester, right, remember the oxygen in an ester is a pi donor, right? So it could donate electron density, right, between these 3 things, right, which would make this significantly less electropositive or partially positive, right? So if a ketone is, partially positive plus plus, we can consider an ester just plus, right? Because we have this pi donation happening, right? Which means this is less partially positive because of that lone pair next to it. If this is less partially positive, that means, well, let me ask you, does it withdraw the negative charge on this carbon better or worse? If it's less partially positive, is it gonna that's a kind of badly phrased question. But it's worse, right? I kind of phrased it bad, but what I meant is like what its ability to withdraw the electron density, right? It's going to be worse because it's not as positive as it can be compared to a ketone because of that ester group here, right? So because it's worse, right? Because it's less partially positive, it stabilizes the negative charge. What's it called? A little bit worse, right? So we could put this as 2 and this is 3, right? Am I saying less positive? I'm saying less positive compared to, yeah, that's what I'm saying. My word choice was not the best there. It's less positive compared to the ketone, right? So for 2 and 3, right, we're kind of comparing the the electron withdrawing effect of the carbonyl, right? So 2, or I should say B and C, right? So B, right, is just the regular old carbonyl, a ketone, right? So if we, let's say, designated that as, partially positive plus plus, right? An ester, right, the carbon in an ester, right, is significantly less partially positive because of this pi donation that happens, right? This is that arrow I showed, right? So if this lone pair is pushing electrons in here, right, basically what that means is that this carbon has more electron density compared to the ketone. If it has more electron density compared to the ketone, it's not going to be as partially positive, which is why I noted it as partially positive with just 1 plus, right? Because of that oxygen, right? But nitrogen, like an amide, is even more, right? And nitrogen's an even better pi donor than oxygen, right? So that kind of, it's like has to do with the reactivity of, carboxylic acid derivatives versus like ketones and aldehydes, right? And because of that, if it's less positive, right, its withdrawing effect is not going to be as good, right? If its withdrawing effect is not as good, that means the lone pair is not really well stabilized. If the lone pair is not well stabilized, that means the original molecule is not very acidic, right? So that's the logic you would use there. Well, kind of similar. The difference is it's still electron withdrawing because remember, the negative charge is still next to a carbonyl. It's just not as much, right? There's a difference here, right? There's no electron withdrawing happening here, right? This is a electron-rich group. Here, we're just comparing the differences of these electron withdrawing group. Which one is more electron withdrawing? In a regular carbonyl, right, a ketone or aldehyde is more electron withdrawing than an ester, right? Because that carbon is not as positive, or not as positive in the esters or amides, right? So if you want to kind of review this would be in, I guess, chapter 20, right? That was the carboxylic acid chapter, right? It has to do with the reactivity and electrophilicity of carboxylic acid derivatives, right? So yeah, that's the logic you would use there. Okay.
Sharo,
Yeah.
I have a question. So, but not about this problem, the previous one.
Yeah.
So in the book there was similar problem, but they had like ethanol and the other one where you have acetyl acid. Yeah, instead of methanol, you had like ethanol, and you have obviously acetyl acetone.
Yeah.
They did give priority for acetyl acetone over the ethanol. Shouldn't be the same logic.
For what? So which one would it be? Like C versus which one are you talking about?
C versus D. They gave D priority over C when C was ethanol.
So they made C more acidic, or
no? They made D more
acidic,
and the C less
Let's see.
acidic.
The logic I used is Ario, right? Because without number. That's why I said to ask your professor this one specifically, right? Because that's why when I scrolled back up, because you see here it's just regular ketone groups. Here it's esters, right? So personally, I would think anything on an oxygen is just much more acidic because it's on an oxygen versus a carbon. Maybe if someone did a paper on this, right, you could technically be like, oh, you know, this was proven to be more acidic. That's why this kind of gets a little messy here. But I would just use the basic Ariel logic. That might
But
be wrong, right? So that's why I said confirm with your professor tomorrow if you have a chance to see if that's right. I just used, you know, what I've always been doing, right? Is that this is on an oxygen. I automatically expect anything on an oxygen to be more acidic, right? But obviously, if you have two electron withdrawing groups, maybe things can change, right? So that's why I said maybe double check that with your professor. That's the logic I would use. Hopefully, I get all the points if I did. Yeah, that's my logic for that question. Maybe technically two electron withdrawing groups make it more acidic. I don't know. I mean, generally, I would always think anything on a nitrogen or oxygen is going to be more acidic than anything on a carbon. But like I said, this is stuff that, you know, you could, you know, write a paper about and be like, oh, this, you know, malonic ester was the proton was found to be more acidic than that of methanol and ethanol or whatever it is. So double check that with your professor. Let me actually look up. Okay. Ethyl. I'm going to look up actual pKa values. Diethyl malonate. So, sorry, no, I need dimethyl malonate, but that should be the same. So pKa, I don't have a pKa for that. Damn. Diethyl malonate has a pKa of 14 and methanol is like 15 or something like that. So technically it is more, if you had ETs here, but that would just make this one similar too. So yeah, confirm this with your professor. Maybe 1 and 2 are switched here, right? Like I said, this is, you know, it's the whole issue with the, you know, acidity questions like that is maybe something might take precedence over. I just stuck to what I've always done, right? So confirm that with your professor. But the other two should be as is though, right? The aldehyde's going to be the worst. Ketone, not as much. I guess is really just methanol versus that. Okay. Let's keep on keeping on then. Let's do. I'm just gonna skip 4. That is literally just reactions, right? So for, I guess for 2019 exam PR, if you have solutions, feel free to message them to me or like post them in the group chat to share with others. Me, look over them because this is gonna just take forever to do. I'd rather do the other questions. Okay, let's see, what is this? Okay, we'll do the mechanism question, I guess. It's not too bad. Just form a diol. Okay, let's do that one. So this is 18. ST number 5. Do A first. Oh man, the other one is super simple too. B is literally just a aldol condensation, or whatever you want to call it. Yeah, it's aldol condensation A. I mean, yeah, if I was taking this exam, I'd pick B because that's 100% easier. Okay, let's do this. So this is this phenyl ring. This is going to be a bunch of stuff. OH. You have O and OH. Make that ring like that. And then you have a methyl group here. Okay, so let's see what changed, right? Oh, sorry, I have to give you guys the other molecule. H2O. You know, all that really happened here is it's essentially just proton transfers, but you're just using a base to do it, right? So if you look at this, right, let's zoom out a little, right? This and this group, obviously, let's circle maybe this in orange in this group. Oh, oops, missing a methyl, right? So you're turning the first, I guess, hydroxyl group into a ketone, right? So essentially, this is kind of like a dual tautomerization, right? Where really what you're doing is you're kind of tautomerizing from one side to the next side, right? So we're gonna essentially start from here, right? This one here, right? We're gonna tautomerize this into its enol, right? Well, kind of its enol. Technically, it'll probably just stay as alkene, right? And then we're just essentially what we're doing is we're just moving this double bond around, right? It's going to move from here, 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 right? And that's really what you have to notice here, right? Let's say like, you know, you guys have access to answer key and all this stuff, but let's say you saw this on exam, what you would look at here, right, is what changed. And that's what I said is you could think of this as a proton transfers, right? It's just the proton is moving around the molecule, or you could think of that conjugation as just changing, right? So the first thing, right, that you want to do here, right, is get this carbonyl into this OH, right? And we know we could easily do that, right? By doing base like a enolate formation, right? So we're under basic conditions, so we're not going to go through regular enols. We're going to go through base. So that's another thing in terms of a mechanism. You should never get a positive charge in this mechanism, right? This mechanism should all be negative charge. So that's another kind of hint towards the mechanism. Basic conditions, right? You should never have if you formed a positive charge at some point, probably messed up, right? So once you take those two things into consideration, then you could kind of get started. So let's start down here. H. Okay, so we are moving it from right to left, right? So technically we do have a proton here, but we're not trying to form an enol with that side, right? Because that's not going to lead us to forming a carbonyl on the left carbon, right? So I guess the first thing you will do is you grab the alpha proton on the left-hand side of this, right? Guess I'll just go down and let me draw it on this side then. HO minus. Well, that's the thing. Technically, it goes through E1CB, so I'm gonna leave it in its regular form. So what I was trying to do was just do it. I was trying to immediately just go towards the O minus here, right? So I was gonna push this here and like this. But the thing is, like, this is that one of those mechanisms you guys learned is E1CB, right? So we need to form a carbon ion, right? So I guess we should start off with this. Otherwise, it would be like E2 something. Okay, we have OH here. Now we have this and this. Oh, that should still be a carbonyl. My bad. There we go. Now we could push it, right? So just to be clear why this is two distinct steps is because this is technically like it's the reverse, I guess, technically of an E1CB, right? So you want to show the carbon ion. It doesn't happen concertedly, right? This is going to form because technically we could isolate this, right? And the reason why we could isolate this is if you introduced any electrophile into the solution, 100% you'd get a trapped species, right? Where whatever this electrophile is will be attached there, right? So that's why we have to form the carbon ion. Okay, now this, oh, oops, let's stick to the orange arrows. We will push here and we'll push here. Once again, same thing. Everything is going to have either a negative or a neutral charge. At no point should we ever form a positive charge. I can't iterate that enough because if he sees that, he's going to understand you don't really know what's going on, right? And that's one of those things I mentioned in the beginning of the semester was acidic conditions, neutral or positive charges, basic conditions, neutral or negative charges, right? So OH, now we have this kind of weird geminal diol. No, this shouldn't be OH yet. It should be O minus first. And then we just protonate. I was going to write H plus like I normally do. And then I was like, wait, we're in acidic conditions. Can't do that right now. I mean, we're in basic conditions. We can't put this H plus in there. Then this goes here, forms more base. Man, it's going to get long. Let's go down this way. Actually, you know what? I'm just going to go to the side. I'm just going to keep scrolling. Oops. So then when you guys want to look at this later, you can just side scroll. Okay. OH. 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 Right? Methyl. I keep forgetting that methyl. Let's go down. I keep going this way. Once again, I'm saying that's what I was saying is it's reverse of an enol, right? So it's literally just continuous tautomerization, this mechanism, right? So now we formed our first enol. Now we could reverse this enol, right? So it's really just it's literally just like three consecutive tautomerizations, right? Now we're gonna turn this eol into a carbonyl, right? And then we could turn it onto the enol on the other side, right? And that's all that's happened. That's why I said it's really just, if you looked at it, it's just essentially moving that double bond across those atoms, right? That's all that's happening, right? That's the only difference in the structures, right? So it's just because of this, the way these OHs are positioned, they could do this, right? So now next step is turning this into a carbonyl, right? And then turning it into an enol on the other side. And then the final step will be turning that enol into its carbonyl form, right? So next step, we have to deprotonate that on the bottom. Go here, actually draw this out. And this is going to go here. You know what, maybe let's go down now so it doesn't get too long. Minus, and what are we missing? Methyl and double bond. Okay, now we want to reform a carbonyl, right? So you could kind of think of this as two ways, right? Is you could push this here, right? And now this alkene, right? Obviously this carbon is going to have 5 bond. This alkene is very rich now. Voice crack. This alkene's super electron rich, so it's going to find a proton somewhere. We have water here, right? So we can just protonate it, really. That's all. Yeah, that's gonna be the next step, right? So now we protonate that alkene, right? Now we form a carbonyl here, and then we're gonna basically form an enol on the other side. And then once again, same thing. It's literally a repetition of the same movements. It's actually not too bad of a mechanism, but still I would pick B if I would have to, because this question says to choose one. I would personally pick B because that's just a straight up aldol condensation. That should be pretty easy. We've done that in recitation. You've done that in class, right? Okay. HO minus. Actually, no, it would technically be water. Now this protonates this way. And now we have another carbonyl. So now we have the carbonyl in the middle. You know what? I don't know why I've been drawing out this ring. I could literally just write it as pH. OH and carbonyl. Now we're going to form the alkene here, right? So next step is going to be HO minus. It's going to come in, right? Like we did in the first step, right? Was, what did we do in the first step here, right? Right here. We deprotonated that alpha hydrogen. Now, the only difference is this is what we're going to deprotonate, right? So H. Now we're getting very close. Okay. And that's going to push out, right? It's going to form what's it called? We did before, O minus. This gets protonated with water. And like I said before, now our enol is on this side. Now we have another enol, right? And now we're just going to tautomerize this group, and then you get your final thing, right? So same thing as we did in the second part, right? Deprotonate this. Oops. And now reformation, our carbonyl is going to kick in, It's going to get protonated from water. That's going to be our final step. So H2O. And there we go. Final product. Literally just changing, essentially just kind of wiggling around that double bond through the molecule. And once again, I keep forgetting this methyl group and like all these structures. How many did I miss? This one, and this one. And our final answer now. That's it, right? This is kind of ridiculous though. And if only you could just, write taut like this, right? That would make this a lot easier, right? But he wanted to see all electron flow. That's how it would be. I think the only thing he did different was he combined these two steps into one, right? I just kept it like that because it's just how I did it. But that wouldn't be wrong to do it this way either. But yeah, the second one is just the aldol condensation. Could quickly do that one as well, right? Well, actually, technically, it's the reverse of it, right? So we have this conjugated product, the beta unsaturated ketone here, right? Right, so this is this is an alpha beta unsaturated ketone, right? Which we know is a result of aldol condensation, right? So essentially what you're trying to get to is, at one point you're going to have a structure, right, that looks like this, right? So the first thing your goal should be to get towards, right, is like this technically, right? And that's the addition product, right? So this first thing is the condensation product. This is the addition product. So we're basically going in the reverse step, right? So when we learned this, we did the forward reaction, right? Where we deprotonated the alpha proton, attacked the other carbonyl, right? We formed our beta hydroxy ketone, right? Then we, with underwater and heat, we basically deprotonated it, did that whole E1CB, right? And now we're just going in the reverse of all of this. That's all this is, right? So if you remember how that worked, then you should know that the first thing you should try to get towards is something that looks like this, not something that, right? And right here, I should write that it basically said form these two, right? So, okay, now I'm going to erase this and let's start with it. Okay, so if in the last step of a E1CB, right, the OH leaves, right? So recap here, right? Remember E1CB here, right? Whatever carbonyl this might be, right? We have a carbanion that looks like this. Remember the last step is formation of or loss of your leaving group, which is OH minus, right? So the first step here will be OH has to come in, right? Oh, they didn't have to include this, right? So now we're literally doing the reverse of this, right? So nucleophilic attack, exactly, right? And it makes sense because if you look at the products too, right? One of the products here, the 5-membered ring has a carbonyl, right? So we need to do a carbon-oxygen bond at some point, right? So that's going to be the first step, right? So we can go ahead and attack it here, right? We're going to reform our carbanion and let's start heading downwards. Now this is going to get protonated to get our beta hydroxy ketone. I'm sorry if I'm going a little fast, but given that this is recording, you could always watch it later, slowed down, right? But in terms of the recording, everything should be explained. So, but yeah, I am going a bit fast right now. Hopefully, it's not too much of an issue. Okay, so this is what I said we have to get to here, right? Well, no, right? Because remember what I was saying before is the E1CB, right? It happens in a stepwise manner, right? It's not concerted, right? So you want to make sure you show this carbon ion, right? That's essentially what he's looking for, is that you've understood this is the reverse of an aldol condensation, which you know one of the intermediates has to be the carbon ion, right? So make sure you do this in 2 separate steps, right? Okay, now we're gonna split, right? So we're going to first deprotonate. We have, once again, let's say you didn't know anything. You didn't, you were completely a blank slate on this question. Once again, you could use a little bit of logic here, right? Let's say you got stuck here, right? We are under basic conditions, right? We have an alcohol group, right? We formed an alcohol group, right? So if we formed an alcohol group and we're under basic conditions, logically, the next step you could probably do is just deprotonate that and then see where you can go from there, right? So exactly, we're going to be reforming the carbonyl this way, right? And the way we can do that is by deprotoning their, OH, right? And then it's going to reform the carbonyl, split that carbon-carbon bond. And what is it? Oh, Jaro. So we need OH minus. Oops, well. Okay, now we have our O minus formed. And like I said, it's literally just the reverse. Right? Now, next step, right? Reform our carbonyl, because one of our products is a cyclopentanone, right? So here we are literally almost there. What we could do is we need to clearly split those, right? If we reform a carbonyl, right? This is kind of like those what is it? Hydrolysis of like acetals and stuff, right? We're reforming a carbonyl and we're splitting it apart, right? Except the difference is we're splitting a carbon-carbon bond apart, right? So here, that's going to do that. That's going to kick here. Now, once again, form a carbon ion, right? It's not going to do this, right? And that doesn't make sense either because the final product we're trying to look for, right, is a carbonyl there too, right? So it's going to break this bond and it's going to form a enolate, right? And then the other species is already formed at this point, right? So we'll just go this way and we'll split the arrow. So at this point, we formed our cyclopentanone. Oh, let me keep these colors consistent.
Shuruk?
Yeah.
Sorry, I have to leave now.
Okay. Yeah. And there we go. And then the last step is we have water, so you can just protonate and you get your final product. Okay. All right. Yeah, so those are both the mechanisms we worked out. Okay, let's see. Exam. Okay, so let's move on to 6 from exam ST, and then we'll do 7 from exam PR. So have this. Okay, right. Which nitrogen of the fluid, we did this, right? That's why I did those exercises on Saturday. Which nitrogen of the following compound do you expect to be more basic? What do you expect the protonation state of this molecule at physiological pH? So physiological pH is approximately 7.4, right? 7, something like that. But it's basically, I think it's 7.35 to 7.45 with an like around basically 7.4 basic. I keep saying basically. Sorry, I just saw someone said, so question, all these steps are reversible. What do you mean drawn the forward? The forward is just the aldol condensation. With the mechanism, I mean, I don't know if you mean like the equilibrium arrows. I personally, for every mechanism question I've always done, I just always stick with the forward arrows. Even when I did the acetal stuff, I just stuck with the forward arrows. You're not going to lose point on equilibrium arrows. But I don't know if it's reversible. It depends on the kind of temperature and stuff like that. But I mean, yeah, if we're doing the reverse, technically, right, they are in equilibrium with each other. So honestly, I always stick with forward arrows with whatever mechanism it is. I don't want to, plus it's drawing an extra arrow, right? Saves you a second. Where's the nitrogen of the following compound do you expect to be more basic, right? So we did this yesterday, right? More basic means usually more localized or more stable, not stabilized, I guess, less stabilized, right? So here we have two nitrogens, we'll call them A and B, right? This is similar to, not yesterday, I should say Saturday, right? Well, you guys tell me. A, right? So once again, let's review this again, right? If we drew the lone pair here, right? This lone pair here can conjugate this way and this way, right? This can also conjugate this way into the ring, right? So we have a lot of delocalization here. It's a lone pair next to 2 pi bonds, right? B, on the other hand, alkyl group, and it's technically you could consider this semi-alkyl because there's a carbon in between the carbonyl, right? So there's nowhere for this lone pair to go, right? Therefore, it's localized. If it's localized, it's more available to act as a base. It's more available to act as a base. It's going to be more basic, right? So which one of these, right, is going to be this one, right? So for those, when I was saying A, right, review the beginning of the means chapter, right, for looking for localized lone pairs, right? And like stabilizing factors, right? If you have more stabilized, or I should say delocalized lone pairs, it's not going to be as basic because it's not as, the lone pair is not available to act as a base. It's moving around like all this part of the molecule. But if it is stuck at this, the nitrogen, like surrounded by alkyl groups, then it's going to be more basic. So here, all right, more basic. Yeah, exactly, right? And it's got a lot on its plate. So what do you expect the protonation state to be this at physiological pH? Essentially, this is asking is, okay, once you've identified the more basic nitrogen at pH 7, that's about the middle order, right? 7.4 technically, right? 7.4, whatever you want to consider physiological pH. Technically, it's 7.4, right? But it's compared to something, things that are very basic, right? Usually, you like 9, 10, like closer to 14, right, in terms of the pH, right? So if we have something basic in somewhat acidic conditions, right? So when you're close to 7, right, even if it's above 7 or just around that area, you're going to be less basic than any amine, right? So all it's really asking is which nitrogen is going to get protonated, the more basic nitrogen, right? So that's the structure you would draw is just based off your answer to A, right? If you got that correct, right? And technically both get protonated, but essentially what he's looking for is like, once you've identified the more basic one, you know that one is going to get protonated first because it's more basic, right? So the structure would just be, gonna just copy and paste the structure again and then just draw it. Wait a second. Go. And it should just be protonated plus. That's it. So there's that scale, right? pH like 1 to 10, right? You know, when you guys did amino acids, right? Essentially all this is asking is which one of the basic nitrogens is going to get protonated, and the more basic one, because this is kind of in the middle order of pHs, right? But if we went lower than 7, right? So let's say if this was pH 2, right? Then would it just be one nitrogen that gets protonated or both? If we were at pH 2. Be both, because we're in extremely acidic conditions. It doesn't matter how many nitrogens there are. They're all basic enough. I mean, there's enough protons available for them to get protonated, right? So at 7, right, you 7, I guess, kind of like 6.5 to 7.5, that range in terms of like basic atoms. The most basic one will get protonated, right? But once you get lower and lower, anything that can get protonated will get protonated, right? Because you just have that many protons available. Okay, so that was from ST. Let's go on over to PR. LSD, right? The structure of lysergic acid diethylamide, right? What I said? If this is an OH, that's like lysergic acid. So when you have 2 ethyl groups there, diethylamide, right? That's LSD. Fun stuff. Indicate which of the 3 amines is most basic, right? So Jalen there, sorry, just saw this, and this is vice versa. So yeah, when you're extremely basic, right? Everything exactly, right? Because then you're in some conditions where there's a lot of base present, or OH minus, whatever you want to consider basic, right? You have an excess of base. So all the basic stuff will just remain, you know, what I guess neutral technically, and then anything that has acidic protons on it, right, will get deprotonated, right? So actually, technically, this one would actually this would become like an N minus, right? If you had any like OH groups, right, they would become OH minus. Carboxylic acid groups, COO minus, etc. Right? Good point to bring up there. So structure is drawn below, indicate which of the 3 amines is most basic. I'm pretty sure we did this on Saturday, but just for the sake of doing it, we'll do it again, right? We have, technically you have 2 amines and an amide. It's fine, right? Which I guess maybe you meant to write nitrogens, right? So you have this nitrogen, right? You have this nitrogen, right? And we'll call this A, B, and C, right? You guys tell me which one it is. B, right? And hopefully everyone gets it at this point, right? Is it all has to do with localization. Here we are next to alkyl group, alkyl group, alkyl group, right? The carbons next to it have no sort of things. Like technically this pi bond is too far away for it to delocalize. On the amide, right, it can delocalize between the carbon and oxygen. So there is delocalization there. It's not as available, right? And here it can delocalize between these pi bonds or whatever, or this aromatic ring down here, right? So allylic pi bonds next to it and an aromatic ring next to it, right? There's going to be some delocalization on this lone pair, right? Therefore, this one, right, is going to be the most basic. Your reasoning would be it has a localized lone pair because it's surrounded by all alkyl groups. And then you have to mention that the other ones maybe just draw the resonance structures as your explanation, right? This delocalizes with the carbonyl, the other delocalizes with the alkene in the ring, right? Because they're delocalized, they're not as readily available, which means they're much less basic, right? That's it. Okay, so now we'll just do 8, which is the synthesis. So we'll do this from PR, and then there's a peptide one right after it, which I'm pretty sure is the same as the other one. Let me see. Let's look. Yeah, it's the same. I mean, we'll do both, but it's the other question is different. So the malonic ester stuff. So what I will show you is how to approach this if you did get this. Obviously, you could get any synthesis question, but okay. Wait for that to load up. Alrighty. So this is from, 19 PR number 8. So I told you just by looking at it, right? I knew it was similar to the other one because the functionalization is the same. First off, malonic ester, right? One of the main uses we could do from this, right, is we could essentially, through a series of steps, right, install R groups there, right? OET, OET, right? You could have one R group, you could have 2 R groups. It doesn't matter, right? And then we could essentially turn this into a carboxylic acid, right? So basically we could have alkyl substitution, like, or alpha substituted carboxylic acid, right? That's kind of one of its main purposes. It creates that functionalization, right? Yeah. So one of these groups, right, if we hydrolyze this, right, it's gonna turn into, well, when we hydrolyze it, they both turn into carboxylic acid. Then when we heat it enough, right, remember it does that 6-membered transition state, right? And one of the carboxylic acids leaves as, what's it called? CO2, right? And then essentially what this turns into, right, is carboxylic acid with however many R groups. You could have 1, 2, right? Oh, sorry, it should be alpha substituted. So at this position, right? So this is why this was such a useful and still is such a useful reaction, because it allows access to this functionalization, alpha substituted carboxylic acids, right? So if you saw the malonic or the diethyl malonate there, and you knew that one of the really the only reaction we learned with it was to form these types of carboxylic acids, then you could take a look at this amide, right? We know amides, if we go backwards, can come from a carboxylic acid. So if we go backwards, we know we could do a reaction to turn this into that, right? And then we get a molecule that looks like this, right? And now we have our alpha substituted carboxylic acid. And really all you have to do is identify the R groups, right? This R group and this R group, right? So, and then this is what I like I said, I like working backwards and forwards together for synthesis questions, right? So you really already identified all your key intermediates. Now you just have to form them, right? So let's start off with that, right? So, you know what? Let's start off with methyl first, just because it's smaller. It would make a more efficient reaction. So I'm gonna start off with our diethyl malonate. Now, what do we need in order to turn this into a nucleophile here, or turn this here? We need, yeah. Can we use NaOMe or any strong base? Why not? Exactly. So that's a process called transesterification, right? So if you had, let's say, NaOMe, right, you could end up forming a side product with basically OMEs here instead, right? So that's why the base you choose has to be the same as the R group, OR group on the ester, right? So if let's say you got a question like this, but instead of OETs here, it was OMEs, what base would we use here then? NaOMe, right? So I just want to point that out here. Just be careful when you see, if like, we don't know if you're going to get this question for the same malonic ester, but like, you know, the malonic ester isn't limited to diethylmalonate. It could be dimethylmalonate too, right? The only difference is the base you choose has to be the same as the OR group, right? And that's to avoid, oh, oops, what the hell? Damn it, man. Here we go. And that's to avoid the transesterification. Okay, so let's just go back. So go this way, use NaOET. This is our first step, right? That's gonna deprotonate that. We have a nucleophile, right? And we are trying to add, once again, we are adding one. This is this, let me make this blue here, right? Is this carbon, right? So we are only adding one carbon this way. We are only adding 2 carbons. So make sure your carbon count, right? You're not adding 3 carbons or you're not adding 2 carbons, right? Make sure your carbon count is good. Otherwise, you might lose points on that. Now we form this. Okay, now we want to install methyl, right? You could just use methyl bromide, methyl iodide. It really doesn't matter which one you use, right? You know, iodides are technically better, so we'll just use iodides. It doesn't matter. As long as bromides and iodides are both fine for the malonic ester. So we're going to use MEI, right? And now we methylated it. But we're not done here, right? This would be step 2. Now we formed this. We need to install another R group, right? Are we installing ethyl or propyl? Ethyl, right? Let's be careful of that again. Same thing. Now let's go step 3 here. We're going to hit it with the ethoxide again. We are going to form a carbanion. Like I said, I don't think he would take off points if you did the methylation first or the ethylation first, right? I just went methylation because now this is tertiary, right? And methyl is smaller, right? Yeah, I could do that. I'm just drawing it out like this. I don't know. I've numbered all the steps so you could follow through, but you could write it all in one scheme. Yeah, there's nothing wrong with that. I'm just showing the intermediates. Yeah, you could technically just write 4 and just get straight there. I'm just doing it this way just to show every intermediate here. And now we want ethyl iodide. Like I said, iodide or bromide, both are fine. I think the book uses bromide. I know generally in his lecture, he likes using iodides. It doesn't matter. It's just an alkyl halide. Now here, we have our ethyl group, we have our methyl group, and we have our esters. Now, you can just hit this with acid catalyzed hydrolysis with heat, right? So that'd be step 5. So H3O plus, H plus, whatever, heat, right? And the first, technically, what the acid does is turn your esters into carboxylic acid, right? It hydrolyzes your esters. So technically you get OHs. And then what the heat does is it'll let it conform, form that 6-membered state, and basically kick off CO2, right? And then we get our alpha substituted carboxylic acid. So at this point, you should have received a good amount of points for this question. Right now, this is just carboxylic acid chemistry, right? There's nothing wrong with NaOH, right? That's just base hydrolysis of an ester, Nothing wrong with that. Technically, like I said, you could do it all in one step. That wouldn't be wrong. Because remember, esters can be either base hydrolyzed or acid hydrolyzed back into carboxylic acids. Both are acceptable, right? I'm just going to stick with one because it saves me a step, right? This is just carboxylic acid chemistry now, right? You could turn this into an anhydride if you want. You could turn this into, a chloride. You know what? Let's just stick with the chloride. I think he likes doing that as well, right? So if we hit, actually, I don't know why I'm drawing that out. We just need thionyl chloride, right? Sorry, SOCl2 should be step 6, right? So SOCl2, right? Thionyl chloride reacts with carboxylic acids to form an acyl chloride. Acyl chlorides are reactive enough to form amides, right? We are forming NME2, right? So we're going to use a secondary amine, right? So this is the final step 7, right? So we are using, what are we forming? NME2. So you're just doing Me2NH. I don't think you'll need like a conjugate base for, not a conjugate, like a supplementary base for that. It should be fine. Sometimes, you could use pyridine or whatever to pick up the protons, but I think it should be fine. Because technically the base could act as it. And then you get your final product. So this is literally the same. The only difference is the R groups are different from this question to the other question. Boom. Right. And then the last one we're going to do here is peptide synthesis. So this is actually very easy because he only made you make a dipeptide. But this is on both exams. So you think, yeah, I'm pretty sure this is the exact same question on both exams. So should be able to, you should see the answer key, but it's fine either way, right? So we are creating this dipeptide. Whoops. We are creating this dipeptide from this, right? So that's, I think that's alanine. And I want to say, I forget. I honestly forget the name of that one. I don't remember my amino acids. I'm not a biochemist. So we are forming a bond. Let's see, 1 second. Oh, so this is already protected. I didn't even notice, right? So that's already protected as a ester, right? So that's O protected there, which means the O terminus here is doing the attacking on the N terminus here, which means we have to protect the, 1 second. Yeah, I'll just draw it all out. It's fine. How do we do N protection? Valine, I guess that's probably what it's called. Bach, right? So Bach 2O. Right now we have the N terminus protected. So well, that's actually very nice of him to kind of already protect the other one. So you didn't even have to, what's it called? Use like phenol or whatever. Technically. Oh, this wouldn't even be phenol. So it'd be that. That's fine too. It's still O protected. Okay. So we have our methyl here. We have our O minus, right? So now we could add these together, kind of, right? Oh, sorry. This should be N-Bach. Bach-N, right? However you want to write it. And then we add the other part. This what we did at the end of thing. So now we could use DCC for coupling. We get our oops. Oh, sorry. Should be Bach at this point. I was just redrawing that structure. Okay, and then how do we do D protections? Right, yeah, so we have a trifluoroacetic acid, and we also have just base hydrolysis of your ester back into the thing, right? I guess it doesn't matter which order you use, so we could just go downwards, I guess. Yeah, we'll go downwards. So CF3COOH, right? This is TFA, right? That D protects. What does that D protect? The N terminus or O terminus? N, right? And then the second part is base hydrolysis, right? So NaOH. And then you get your final product. Oops. Oh, Jesus. Why is this bugged? Oh, damn it. There we go. Nope, still bugged. Give me a second. There we go. Okay. Okay, that's actually pretty simple. So that's it. No, for synthesis, you don't have to show step by that. He will always specifically say, provide a reasonable, detailed mechanism showing electron flow. That's a mechanism question. When he says provide a synthetic route or a synthetic sequence, something like that, that's just reactions, right? You guys still see the white? Oh, shoot. I'm sorry. I paused the share. Share. My bad. There we go. Yeah, that's the final product. Right? So you just deprotect it, right? That's it. So those are, so like I said, the only thing I would ask is someone brought that up, and then based off the pKa's I looked up, where maybe just ask him to go over that. I mean, guessed off pKa, just because I already saw it on Wikipedia, I would switch out. I would have to make this 2 and 1. Let me make that in orange, right? So this would be 2 and 1 then, right? Based off what I saw on Wikipedia. Like I think this one was 14, this is 15.5, but you can ask him how you drank it. I guess the malanates are more acidic. I just obviously I just assumed, methanol based off it being on oxygen could do that, but yeah, so that's the only one I would ask him, and obviously the ones I didn't cover. But yeah, question 4 is literally, that's just, reaction straight out of your textbook, right? And like to reiterate this, right, in their last exam, a lot of your questions were practice problems, right? So maybe there's a good chance it's gonna be the same. So all I would suggest in between now and the exam, right? And obviously he's gonna do a review tomorrow, is do those practice problems, right? Who knows? Maybe they'll be on the exam. Maybe it'll help you get a better grade, right? Anyways, have a good night. I will see y'all Thursday morning. When's the exam start? 9 o'clock? 9? Or is it 10? Is it 10? Oh, thank God. Okay. I mean, I got to be there early anyways, but I was about to pull up at 8. Thank God. Okay. Yeah, I was going to be there an hour early and just be tight. But